Welcome back everyone. In this lesson we are going to learn about a very special method for spatial systems to solve a simultaneous linear algebraic equations, which is known as the Thomas algorithm. Thomas algorithm was specially designed for tridiagonal system, and we will go through the details of the tridiagonal system and also the Thomas algorithm. So before diving into the details, I want to tell you that there is one special method which is the Gauss-Seidel method, and this Gauss-Seidel method is very popular to solve a simultaneous linear algebraic equations. And we will see that we already have not covered the Gauss-Seidel method, but we will cover this method in our next lessons. And in this lesson, we just want to tell you that the Gauss-Seidel method has some advantages as well as some limitations. In the Gauss-Seidel method, we usually use some initial guesses and iterate through iterations, and that is very problematic, and you will see whenever we cover the Gauss-Seidel method. So I just want to tell you that the Thomas algorithm is specially designed to prefer this method over the Gauss-Seidel method for tridiagonal systems, and we will next see some of the benefits of tridiagonal systems and the Thomas algorithm. So please do not be anxious about the Gauss-Seidel method. We will cover the details in our next lessons. So first let's look at some of the basic ideas of diagonal systems. First of all, let's see what is a banded matrix. Okay, a banded matrix is one where all the diagonal elements and some of the elements in parallel with the principal diagonal are not zero. Okay, so all of the elements except these patch in the matrix are zero. So all these terms are zero, all these elements in this area are zero, and all these elements inside this area are zero. Only the diagonal elements and other elements within this patch are or within this band are not zero. So that's the main theme of banded matrix. So if you want to find out the width of this banded matrix, that means which is BW, it can be denoted as twice HBW plus 1. What is the HBW? HBW is the width of the band in one side. That means in one side of the principal diagonal. So this is the HBW in the upper triangular case, and this is the HBW for the lower triangular case. So there are twice HBW terms and the diagonal term is 1, and that's why this formula comes from. BW equals to twice HBW plus 1. So BW is also known as the bandwidth, and HBW is known as the half bandwidth. Okay, so these two parameters quantify the banded matrix. So if we consider the half bandwidth to be 1 and bandwidth to be 1, in that case there will be 3 elements in the band of the matrix. That means there will be the principal diagonal elements and one element, one band of elements that is parallel to the principal diagonal in the upper triangular, and one parallel band in the lower triangular. That means there will be 3 elements at any row inside this matrix. Okay, that's why it is called a tridiagonal matrix. There are 3 elements along the principal diagonal, so that's why it is called the tridiagonal matrix. So this is a special type of matrix which is frequently occurred in various fields of engineering. For example, it occurs in the if you ever encounter with the quantum mechanics, you will see that the time dependent or time independent Schrodinger equations, whenever we want to solve those time dependent independent Schrodinger equations, we will get such system of equation. That's a tridiagonal system. Also such systems occur in the computational fluid dynamics. If you ever encounter one, you will see that in those cases there are some special examples, special boundary elements, special simulations where these tridiagonal elements occur, and that's why these tridiagonal elements has been a focus of interest for many years, and spatial algorithms were designed to solve such systems. And among them, Thomas algorithm is one of the most very popular one. So we will learn about this algorithm in details in this course, in this lesson. So if you see that most of the elements in a tridiagonal system are 0 except along a band of width 3. So that's why if you use the Gaussian elimination method or the Gauss-Jordan methods, the pivoting elements are not necessary because most of the elements are 0. So you will have only waste lots of amount of time in calculating those rows where most of the elements are 0. So Gaussian elimination and Gauss-Jordan methods are not preferable for such systems where most of the elements are zeros. So that's why we are going to use a Thomas algorithm. Okay, so the tridiagonal banded systems are mostly suitable to be implemented with the Thomas algorithm. Like the LU decomposition method that we have covered so far in the last few lessons, Thomas algorithm also has 3 steps: the decomposition step, the forward substitution, and the backward substitution. So if you remember, the same 3 steps were used for LU decomposition. So if you do not remember, please go through the last couple of lessons to grasp the details of these 3 steps. So let's see how we can use the Thomas algorithm to find out the solutions of a system of linear equations. So this is the pseudocode that I have been providing you. These formulas are for the 3 steps of the Thomas algorithms. We are not going to go into the details of how these formulas are going to be proved. We are just going to use these in our MATLAB course. For example, for decomposition purpose, we use these equations. For forward substitution, we use these equations, and for backward substitution, we use these equations. The forward substitution and the backward substitution, these techniques were already covered in the LU decomposition and Gaussian elimination and Gauss-Jordan methods. So we already know about these courses because we already have implemented those in the LU decomposition or Gaussian elimination method. So the new one is this one, the decomposition part. So let's see how we can use these codes to find out the diagonal elements. So first of all, let's see, the first equation is Ek equal to Ek divided by Fk minus 1. So before, let's say we have the principal diagonal elements denoted by F notations. That means F1, F2, F3, these are the principal diagonal elements. The diagonal elements above the principal diagonals are denoted as G1, G2, G3 up to Gn-1, and the lower diagonal elements below the principal diagonal are denoted as E2, E3, E4 up to En. So these are the notations that we are going to use for our purpose. So look at this, how the Ek terms are calculated. For example, from the original tridiagonal system, we need to decompose, we need to change the matrix into a modified one. And how we are going to modify those values? For example, if we want to modify the value E2 or E3 or E4, that means these lower diagonal elements, those can be modified using these formulas. That means Ek equal to Ek divided by Fk minus 1. For example, you want to determine E2, what we will get? E2 equal to E2 divided by F1. So that means if you want to find out the value of E2, you need to use only these 2 values, E2 and F1. Similarly, if you want to find the value of E3, you need to use these 2 values, E3 and F2. In this way, we can use these 2 values. That means E terms and F terms are combinedly used to find out the values of E terms. Okay. So in this way we can go on. And now see the next equation, which is the f terms. That means we now need to modify the f terms, the principal diagonal elements. And to find out the principal diagonal elements, we need to use the f terms as well as the e terms and g terms. So we need to use all of these three terms to find out a specific f term. For example, if you want to find out the value of f2, you need to use the values of f2, g1 and e2, which are being covered within this red region. Okay, so to find out f2, you need to use the values within this red region. That means e2, f2 and g1. Similarly, if you want to find out the value of f3, which three elements will you use? Yes, exactly, those elements will be e3, f3 and g2. Similarly, we can go on and find out the other f terms. So in this way, we can decompose our original matrix into a Thomas algorithm decomposition technique. And then after the decomposition part, then comes the forward substitution and the backward substitution. And these two steps are the exact same, similar to the LU decomposition technique. So the algorithm can be stated as follows. We can convert the original coefficient matrix A into a modified matrix AM, that we have already said, and to convert all of those elements, we just convert the E terms and the F terms. That means the principal diagonal terms and the diagonal elements below the principal diagonal. We do not convert the G terms. So that's the main difference between the LU decomposition and the Thomas algorithm. We just convert the matrix into a modified matrix AM, and we get this using these two equations, and we get the modified matrix. So once we get the modified matrix, we decompose the modified matrix into the LU decomposition. So in the original LU decomposition method, we converted the original A matrix, the coefficient matrix, into L matrix and U matrix. But now first we have converted the original matrix into a modified one, and then we use the LU decomposition technique to decompose the modified matrix into the lower triangular matrix and the upper triangular matrix. So that's the difference between the Thomas algorithm and the LU decomposition technique. After that, once we get the LU decomposition, we use the lower triangular matrix, and the R is the constant vector. Here R is the constant vector. In the previous case, in original LU decomposition, we use the B notation, but right now we are using the smaller notations. And also in the original LU decomposition technique, we denoted the intermediate solutions to be the D matrix, but right now we are using the R matrix. But those are actually the same equations, the same formula, the same procedure. We are just denoting with different notations. B, small r for B, and capital R for D. So using these formula, we determine the intermediate solutions of R matrix, and once we get the R matrix, and in the step 4, using this formula, we can determine the values of the original unknown variables, which is denoted as the T vector. So T is our original unknown variables that we are going to determine. So that's the Thomas algorithm. Is very straightforward, which is very at least I would say it's very exact to the LU decomposition method, just with an extension of a single step. We just modified the original matrix into a converted matrix. So that's the difference. So let's look at an example. Say we have a tri-diagonal system which looks like this. Okay, there are 3 elements at each row, and all the other elements are zeros. Although zeros are not specified here, but you have to assume that those are zeros. So this is a tri-diagonal system. Our unknown variables are T1, T2, T3 and T4, and the constant matrix is this one. So what we are going to do, we first take the coefficient matrix, that means this tri-diagonal matrix. We convert this matrix into our modified matrix using the equations that we have seen in our algorithm. So how we are going to use those equations? These 2 equations that we are going to use, we are going to convert the lower diagonal elements and the principal diagonal elements. We are not going to touch the upper triangular elements. Those would remain the same. So to to convert the lower triangular elements, we use this formula, ek equal to ek divided by fk minus 1, this upper formula. And to convert the principal diagonal elements, we use this formula. So how we are going to use, let's say we want to find out the value of E2. Okay, to find out the E2 is denoted as E2 equal to E2 divided by F1. What is the E2? E2 is minus 1, which is this one. And then what is the F1? F1 is 2.04. So if we divide the minus 1 with the 2.04, that means E2 divided by F1, we will get the result minus 0.49. So that is the E2, that means our modified E2 term. In this way we can use the F equation, that means this one, Fk equal to Fk minus Ck times Tk minus 1. Let's say we want to modify this term F2. Okay, we want to modify this term F2. F2 is 2.04. So in order to find out the modified version of F2, we use this formula, that means F2 equal to F2 minus E2 times G1. What is F2? F2 is 2.04. What is E2? E2 is this one, that means we have already determined the modified version, which is minus 0.49. Okay, we remember we are not using the original E2 because we already have determined the modified version of E2, that means minus 0.49. So this minus 1 will no longer be used in our later calculations. We will use the modified one with that we have already determined. Okay, so this is a dynamic approach. We determine one value and using those values we determine the subsequent values. So this is a dynamic approach. So let's see, here we have substituted the F2 value, which is 2.04. Then we have used minus E2. What is E2? E2 is minus 0.49 times G1. What is G1? G1 is this, which is minus 1. So after calculating these values, we will get the F2 value, which is 1.550. Similarly, we can determine the other values E3, F3, E4, F4 and other terms. So we have got our final modified matrix, which is something like this, AM equal to this. And remember, we do not need to modify the F1 term, because to find out the F1 term we need to use the G0, but there is no G0 term. Okay, so that's why these F1 terms remains the same as we had in the original matrix. So this is our modified matrix. So once we get our modified matrix, we will use the LU decomposition. So how do you use the LU decomposition? For tridiagonal system, the LU decomposition is very straightforward. You do not need to use the Gaussian elimination for tridiagonal system. We can easily determine the LU decomposition from with just visual inspection. For example, look at this. In the lower triangular element, if we consider the lower triangular element, that is the L matrix. Okay, that is the L matrix. That means look at this, minus 0.49, minus 0.49, minus 0.645, minus 0.645, and this one is also calculated here. And this one, these three elements denote the lower triangular elements. Okay, this one denotes the lower triangular elements, and what would be the upper triangular elements? We just consider the upper triangular elements, which we consider the principal diagonal element and the diagonal element that is upper to the principal diagonal. That means this one, this green matrix, this green triangular shape region denotes the elements that are going to be present in the upper triangular matrix. Okay, remember, in the lower triangular matrix we just considered the lower elements and we just substituted the principal diagonal elements with just 1. That's the main difference here. So just using just visual inspection, we can easily determine the lower triangular matrix and the upper triangular matrix. So if we multiply those two matrices, we can easily get back to the modified matrix. That means the original matrix here. So once we get the lower triangular matrix and the upper triangular matrix, from the step 3 of Thomas algorithm, we can use this formula. What is this formula? The R matrix, the R vector, this is the original constant vector from our example, and this L terms denotes the lower triangular matrix, and this R is the intermediate solutions, and that's what we are going to find out. To find out the R matrix, we can use the forward substitution method. So I have just used a single step to multiply and use the forward substitution method. So you just go through the standard procedure to find out the forward substitution, to find out the R matrix, that R matrix element, the intermediate solution elements. So this is the just a simple forward substitution method. I have just used a shortcut, so do not be overwhelmed by these equations. This is just a simple straightforward forward substitution. For example, we have just determined the first element, that means R1, which is 40.8, and using that value we determined the R2, which is 20.8, and then we determine the R3 and R4 terms. So this is just forward substitution method you can determine. Next, in the last step, in the step 4 of Thomas algorithm, we can use the backward substitution to find out our original solution of the unknown variable. So this is the equation that we are going to use in the last step. We have already determined the intermediate solutions here, R1, R2, R3 and R4, and we already have determined the upper triangular matrix. So using backward substitution, we can easily determine these values, T1, T2, T3, T4. So again, this is just a shortcut approach, so you do not need to be overwhelmed about seeing these calculations. You just go through the normal procedure of backward substitution that we used for Gaussian elimination. So that's the same procedure here. So T1, T2, T3, T4, these are our final solutions. So Thomas algorithm was specially developed for tri-diagonal system. It is suitable for computational implementation. So that's the main purpose of using Thomas algorithm. You do not need to use the Gaussian elimination, Gauss-Jordan or Gauss-Seidel methods. Those are very much computationally loss of time and loss of effort, because there are most of the elements of the tri-diagonal system are zeros, as we have already said. So with zeros elements, you do not need to calculate the pivoting or pivot equations. You do not need to consider this. Also, it might happen that you encounter a situation where the pivot elements becomes zero, no matter whether you do partial pivoting or complete pivoting. So that's why sometimes the Gauss-Jordan eliminations or Gaussian elimination, those methods are not preferable for tri-diagonal systems. So in this lesson, we have learned about a special method, which is Thomas algorithm, which is specially designed for special purposes like computational fluid dynamics or quantum mechanics, so solution of Schrodinger equations. So this method is very much effective for those cases. So if you ever encounter in your research or engineering life, if you want to if you want to solve for tri-diagonal systems, you can go through the Thomas algorithm at first. So that's how we use the Thomas algorithm. Please try out the MATLAB code that I have attached with this lesson that implements the Thomas algorithm. Although I want to ask you to implement this Thomas algorithm by yourself, because this is the same method as the LU decomposition method, except there is a first step where we convert the original coefficient matrix into a modified matrix. So that's the main difference between the LU decomposition and the Thomas algorithm. So in the next lesson, as we have promised, we will learn about the Gauss-Seidel method. The Gauss-Seidel method is another dynamic approach which is very much also suitable for computational implementations. It's more preferable than the Gauss-Jordan or Gaussian elimination method. We will go through the details of this method in the next lesson. So till then, thank you so much.